Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. So we are still in the initial phase of this course, and what we have just seen thus far is that, well, if you have a very complicated system, then there's a way of pulling out the complicated part of the dynamics and separating it out from the linearized part or the linear part of the dynamical system. And then we claimed that this complicated part, even though it cannot be mapped as a linear part, a single linear map, but it can be mapped or it can be represented as a collection of linear maps, a set of linear maps, right? And in so suggesting, it becomes then imperative that we try and understand about what these linear maps are all about. In our quest to understand linear maps better, it turned out that we need to resort to certain concepts from linear algebra, and down the way we have seen ideas like what's a vector space. We haven't delved so much into what a field is. We have assume that you have a fairly good understanding of what a field generally is like from our basic understanding of real numbers and complex numbers, which are basically the fields that we will be dealing with in this course. Nonetheless, so we started with this notion of what a vector space is, then we saw notions like linear independence, basis, a spanning set, right? And then we also saw what is an ordered basis, right? So if you give a particular indexing to these members of the basis set, of course I am talking about a finite dimensional vector space there, right? Then we get what is an ordered basis. And once you have got an ordered basis for a finite dimensional vector space, it turns out that every vector in that vector space can then be represented like elements in a Euclidean space, in an n-dimensional Euclidean space, that is by a column of n numbers, and n tuple is what we call it. Yeah, and it behaves exactly like you would expect a point on the Euclidean space to behave, right? But of course, the groundwork for that is we have to have an ordered basis, and we know then that the representation of any vector in terms of a basis, let alone an ordered basis, is always going to be unique, right? So that allows us to push this idea forward. Now in this lecture we shall delve further into these topics from linear algebra, again not very rigorously, but maybe semi-rigorously, and we will give some of the proofs, and some other proofs we will probably ask you to look up from some standard textbooks. So we will sort of have to make some compromises down the way. We cannot make this a complete hardcore linear algebra course, right? Okay, so to refresh your memory, recall that in the last lecture we have seen that when you have an ordered basis, any vector in a vector space V can be represented in terms of the ordered basis by a column of numbers, right? So it's like it's coming from the field Fn, where F is the field. In our case, F would be either R or C, real numbers or complex numbers. So we have sort of agreed, at least up until this point, that our treatment or whatever we have suggested is beyond any doubt, right? Now it is time to make the next push, right? Having defined what these coordinates are, we are now going to study what these objects called linear maps are going to be like, okay? Linear maps. So what are linear maps? Linear maps are basically maps from one vector space to another, satisfying certain properties. So suppose I have a linear map from a vector space V to the vector space W, right. Remember this V and this W, these are vector spaces, okay, over some field either R or C in our case, okay. Could be a general field, but again we will not really get into too much of those nitty-gritties, right. So, it is a mapping from a vector space V to this vector space W, satisfying, very important, the following property. The following property. And what is that property? That is, suppose you take a vector alpha times V1 plus beta times V2, right, and operate using this map on this vector. So, remember, let me just mark it out for you. So, this belongs to F, again that F in our case will be R or C, I will never grow tired of saying this, right. Again this beta, this also comes from F. Now, V1, this comes from the domain, as does V2, okay. So, you take elements V1 and V2 from the vector space, you take elements alpha and beta from the field, right. Then you know that the scalar multiplication we have already defined, it is necessary. So, this is the scalar multiplication that we have defined on the vector space, right, and this is the vector addition that we have defined in the vector space. Remember that vector space definition within itself contained the description of a field, a set V, and these two operations which satisfied certain properties like closure, identity, existence of identity, existence of an inverse, associativity, commutativity, distributivity with respect to those two operations, so on and so forth, right. So, all those properties were satisfied. So, of course, we understand what this scalar multiplication is the moment we understand what the vector space is, and of course, we also understand what this vector addition is. And because of the closure property, you should just convince yourself that this element that we are picking out now, this whole element that we are picking out now, right, this fellow in its entirety comes from V. So, that when we are saying that A is a mapping from V to W, you must pick out an element from V and only then can you operate A on it, right. You cannot pick out any arbitrary element from any other vector space or any set and say that I am allowing A to act on it. That element must belong to V in the first place, right. And about this element, this alpha V1 plus beta V2, there is no doubt that it belongs to the vector space V, okay, right. So, then you act on that element and it will satisfy the following property. This is the quintessential property of a linear map, that is, it is going to be alpha times A V1 plus beta times A V2, okay. What does that mean? Notice here, this particular element, this A V1, where does this belong to? If V comes from the set, V1 comes from the set V, then A V1, that is, when V1 is mapped using A, this comes from the set or the vector space W, as does A V2, okay. So, now you have A V1 belonging to W, A V2 belonging to W. So, what is this scalar multiplication then? This scalar multiplication is as per the rules in the vector space W, right. So, this is the operation as defined by the vector space W. Yeah, here all these were addition and multiplication, scalar multiplication, these were all as per the definition in the vector space V, right. So, all that it says is that, well, if you take a linear combination, okay, if you take a linear combination of vectors in the domain and then acted on using a map, a linear map on that element, which is a linear combination of certain elements in the domain, then what you get back is a linear combination, the same linear combination in fact, in some sense. By same I mean that you first get this linear map to act on those individual elements in the domain and then take their linear combination. It would be the same as, now the second linear combination by the way is happening in W, right. So, on the right hand side this is a linear combination of elements in W. On the other hand, this yellow part what I have marked out here is a linear combination of elements in V. So, whether you take first a linear combination of elements in V and then get this linear map to act on it, it would be the same if you had not done that and instead you had gotten these individual elements to be acted upon, these individual elements in V to be acted upon by the linear map, and then taken their linear combination in W, right. So, that is the defining property of a linear map. Okay. So, I may be seen to be harping a little bit on these things, yeah, to the point of being utterly repetitive, but it is very important to understand, right. At the heart of linearity is this property, this linear map, yeah, because everything that we have done, everything that we will do in this course when we define a linear system, right, typically in a state space notation what we do is x dot is equal to ax plus bu, right. So, it is important to understand that what we are doing there, that ax, when A is a matrix, as I promised you later, we will see that very shortly now, that a linear map from a finite dimensional vector space to another is essentially nothing but a matrix. It can be represented as nothing but a matrix. Once you agree with that, coordinate representation of vectors in a finite dimensional vector space, right. So, then you will begin to see all of these things in a new light, and then you will understand that all we have been dealing with so far in maybe our earlier control theory courses at the undergraduate level, they were all basically linear maps, and therefore, it is imperative that we have a deep understanding of matrices, yeah, because at the heart of every linear map is at the end of the day a matrix or the other. It is only that you have to know how to massage it around in a pliable form so that you get the requisite matrix. Okay. Of course, it need not be emphasized, I mean I cannot emphasize this too much, that this linear map representation heavily depends on the basis that you have chosen. We will see all of that in much greater rigor, but it helps to keep these little bit of things, little bits and pieces of these things in mind as we embark on this, on our quest to describe a linear map. Okay. Right. So, what is the next best thing that we should look at? How are we going to represent a linear map from an abstract vector space to another as mere matrices from one Euclidean space to another, or maybe one n-dimensional complex space to another. Yeah. So, let us try and have a look at this. Okay. So, suppose you have this V. So, I am not going to write everything down, you can fill in the gaps where I am saying things in words. Yeah. So, suppose this B has a basis that is given by V1, V2 dot 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 till Vn. Okay. And similarly, W has a basis that is given by W1, W2 dot 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 through till Wm. All right. So, now what do we say about this? How do we describe a linear map? So, suppose A is a linear map from this V to this W. Okay. So, pick any element in V. Now, since the basis is a spanning set, say small v. Okay. So, then we can write V as a linear combination of elements in the basis set BV, right. So, let us just write this as alpha 1 V1 plus alpha 2 V2, and very important, let this also be an ordered basis. Okay. Both of these, let both of these be ordered basis, so that I cannot permute this. If I permute this, it becomes a different basis. Okay. So, this is not invariant to permutation. That is when I have imposed the order on this basis, that is what it basically means. Okay. So, now suppose I let A act on V, then by the linearity property that we have just described for a linear map, what does this mean? This means that this is going to be nothing but A acting on this fellow alpha 1 V1 plus alpha 2 V2 plus dot 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 till alpha n Vn. Now I invoke the linearity property. So remember that this scalar multiplication is happening in V, but I have seen that whether I do the scalar multiplication in V and then pass it through the linear map, or I first pass each individual element through a linear map and then do the scalar multiplication in W, it matters not insofar as a linear map is concerned, right. So therefore, I can now write this as alpha 1 AV1. So remember, this scalar multiplication is now in W, alpha 2 AV2, so on and so forth till alpha n AVN, right. So I can do this, okay, without violating any of the tenets. But now notice that this is something that belongs to W, right, because after all A's basic task is that it maps something in V to something in W. So this belongs to W. So if this belongs to W, then it also has a representation in terms of the basis, the ordered basis BW, because once, see, originally V could be represented as a linear combination of elements in V, the vector space V, but once I have allowed A to act on V, now this is an element in W. So clearly this has a unique representation in terms of the basis elements in W, right. So therefore this can now be written as, if I write it in this fashion, it can be written as beta 1 W1 plus beta 2 W2 plus beta m Wm, all right. Okay, good. So now what have we here? Yeah. Now suppose I choose some very special elements now, okay. Suppose when you allow this linear map to act on the kth element, be very careful about this. What is this Vk? It makes sense to talk about the kth element because this is an ordered basis. So you cannot just arbitrarily assign any one of them as the first element, any one of them as the second element. Once you have fixed it up and you've called it an ordered basis, then the order gets fixed up, right. So it makes sense to talk about the kth element in the basis. Unless it is an ordered basis, it doesn't make sense. So that's why that ordered basis part is very important. So now suppose I know, right, and this is again a very important feature, and that's why it's beautiful, right, because once you know, and this is a very crucial statement, once you know what a linear map does to elements in a basis set of the domain, you know what that linear map does to every other element in that domain. That is the beauty of a linear map. That's why we love working with linear maps, right. That's why when we had this complicated dynamical system, we are always so keen to pull out the linear part from the complicated dynamics and then get an approximation or an sort of a over approximation of the complicated dynamics using multiple linear maps, because even if it is not a single linear map, even if it's multiple linear maps, at least we know how to figure them out, at least we know how to deal with them, yeah, because just by knowing what it does to a finite number of fellows in a finite dimensional vector space, we know what it does to every other fellow. I'm talking about a linear map, that is, right. So that's the beautiful thing. Now suppose I know, right, that every time you allow this linear map A to act on the kth element of the basis set in V, that is BV, here this BV, right, then this is what it does to it. Now if it's a linear map, then what can it at most do? Remember that this is some element in W, no? So if this is some element in W, this has a representation in W, right? But what can it do to the element Vk from this basis set when it acts on it, right? So if this is something that belongs to W, then I can as well write it as a linear combination of the elements in BW, right? If it's just a bit of bookkeeping, you see, I just have to know that V belongs to any element small v, V1, V2, Vk, whatever I am describing, these belong to the vector space big V, but once they are acted upon by this linear map, then they start belonging to the vector space W, yeah, the codomain, So, now I can write this as suppose. So, every element in W has a unique representation in terms of this ordered basis BW that I have defined. So, suppose that representation is given by A 1k W1 plus A 2k W2 plus dot 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 till A mk Wm. Yeah, because there are only m fellows in the basis set for the vector space W, right. So, this I know to be true. Okay. So, now what can I write this as? Remember this, right. Let me use a different color here to highlight this part of the equation. So, remember this box part and this part. Yeah. So, what we are going to make use of is this box part. This is equal to this, right. Furthermore, once we have knowledge about the fact that every such member in the basis BV, when acted upon by this linear map A, yields a vector in W, which is a linear combination of the elements in the basis for W, that is BW, in this fashion, then what can we write? Yeah. Now, therefore, we can say, look, I have that alpha times alpha times A V1, I am missing out the index, excuse me. So, it is alpha 1 times, yeah, that is correct. So, alpha 1 times A V1 plus alpha 2 times A V2 plus dot 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 till alpha n times A V n. That is nothing but just a rewriting of this, no? Just a rewriting of this line. Yeah. This is equal to what? This is equal to beta 1 W1 plus beta 2 W2 plus dot 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 till beta m Wm. Just combining these, yeah, these two steps, or maybe even these two steps, whatever you will. But now, further, now I am going to use this fact here, this star, let me put it as a double star. Further, this double star dictates that this alpha 1 times A V1 is equal to nothing but alpha 1 times, notice very carefully, I am just going to replace k with 1 here. So, it is going to be A 11 W1, yeah, plus A 21 W2 plus dot 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 till A M1 Wm, yeah, just replacing this k with 1 here. Similarly, if I go like this, then I get alpha n times A V n is equal to alpha n times, I am just going to represent this. So, this is whatever is in the third bracket. So, here also this is whatever is there in the third bracket. So, this is going to be alpha, hang on, n, or rather this is not alpha, sorry, this is A. So, remember what is this expression? The first one is the running coordinate, running variable. So, A 1n, A 1n W1 plus A 2n W2 plus dot 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 till A mn Wm, all right. So, remember there are n such lines. So, adding all of these together on both sides, yeah, on the left hand side what do I have? On the left hand side I have, summation beta I Wi I going from 1 through m, And on the right hand side what do I have? Look, if I were to isolate the coefficients of W1, what would I get? I would get W1 and then within bracket I have A11 alpha 1, A11 alpha 1 plus potentially A12 alpha 2 plus dot 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 till A1n alpha n. Yeah. Similarly, plus if I write W2, I would get A21 alpha 1 plus A22 alpha 2 plus dot 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 till I get A2n alpha n. Likewise, plus till I write Wm, yeah, then I get A m1 alpha 1 plus A m2 alpha 2 plus dot 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 till plus A mn alpha n. And now, because this set W1 through Wm is linearly independent, I can just write from this that if I put all of these, so remember if I bring every term to the left hand side of this equality here in this expression, then what I get is that I have a linear combination of terms like W1, W2, W3 such that it yields 0. But since they are linearly independent, therefore every coefficient must be 0. So I can then write that beta I minus, and notice very carefully what this is, summation ai k alpha k, k going from 1 through n is equal to 0. Why? Due to linear independence of the basis set BW, right. So, if I want to write this now, if I want to represent this now, what is this? What are these betas after all? Remember, what are these betas? The betas are the representation of AV in terms of the ordered basis BW, right. So, if you would allow me to write it in this fashion, I would say that AV represented in terms of the basis BW is going to be beta 1, beta 2 dot 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 till beta m, and this belongs to f to the m, right. So, remember AV belongs to W and this AV represented in this coordinate form here, this belongs to Fm, and this mapping is possible, this representation is possible only subject to the existence of such a ordered basis, such an ordered basis. Okay. On the other hand, what about the alphas? If I take V and if I wanted to represent V in terms of the basis BV, then wouldn't I have also written it as alpha 1, alpha 2 dot 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 until alpha n? Because remember, this representation here is subject to an ordered basis BV. So, if I want to get a coordinate representation of this V, this is how I do it, right. This of course belongs to Fn, right. So, now it seems very familiar therefore, right. What is beta 1? So, beta 1, beta 2 dot 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 till beta m, I can then write this as, let me just open it up a bit and write it down and that will be clear. This is summation over k, right. So, it is A11 alpha 1 plus A12 alpha 2 plus dot 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 till A1n alpha n. Next one is A21 alpha 1 plus A22 alpha 2 plus dot 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 till A2n alpha n. Likewise, the last one is A m1 alpha 1 plus A m2 alpha 2 plus dot 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 till A mn alpha n. But this we already know how to write this in a familiar fashion, no? Just focus on any one of these terms here, maybe a term such as this. This, as a side note, I put it to you, can be written as a11 dot dot dot, or rather a11, a12 dot 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 till a1n, a row vector times the column vector alpha 1 alpha 2 dot 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 till alpha n, right. So, therefore, I might as well express the left hand side in the following fashion, right, which is a11 a12 dot 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 till a1n, a21 a22 dot 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 till a2n, right, till I get here last am1 am2 dot 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 till amn, and this is alpha 1 alpha 2 dot 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 till alpha n, all right. But what is this after all? If I now look at this object on the left hand side, this is nothing but AV represented in terms of the basis of W. If I look at this object on the right hand side, this is nothing but V represented in terms of the basis for the ordered basis for V. And this is an object that we are all very familiar with, nothing but an M cross N matrix. Yeah. So, once you have represented objects in vector spaces as through a coordinate transformation in terms of these ordered bases, then it turns out that a linear map between two abstract vector spaces is nothing but a matrix equivalent to a matrix between two spaces that are represented as n tuples of numbers or columns of numbers, right. So, therefore, this object we call as the representation of A, okay. The matrix representation of the operator, or sorry, not the operator, the matrix representation of the linear map A, and we put a box bracket next to it. Of course, it is a matter of notation or convenience, therefore, I mean some people use a box bracket, some people just use the same notation just to describe an operator as well as to describe the corresponding matrix for that operator, or the the linear map. When I say operator, it basically means that V and W are the same. So, when your domain and the codomain are the same vector space, then the linear map is said to be an operator, a linear operator. Okay. So, that is why this operator is slipping into my speech quite often, maybe a little incorrectly in this context, because we have not assumed that M is equal to N here, right. We have not assumed that V and W are the same vector space, right. They are allowed to be different vector spaces, in which case the dimensions could also be different, and therefore, this matrix need not be a square matrix, right. So, having seen this, this is beautiful, because now this motivates us to sort of study matrices in much greater detail, because once we have seen that mapping, a linear mapping between two vector spaces is after all, two finite dimensional vector spaces is after all nothing but the study of a matrix. So, therefore, we need to understand matrices in much greater detail to be able to encapsulate whatever is part of this particular course, right. So, let us try to understand, let us try to dig a little deeper into some features, some important properties of this linear map. Okay. So, one of the important properties are, or some of the important properties are like some important subspaces associated with a linear map. Okay. So, the first important subspace that you will associate with a linear map is, so let us just give it a heading, subspaces associated with a linear map, all right. So, the first important subspace associated with a linear map would be the image. So, I myself will be guilty of this notational abuse or abuse of notation. So, I shall not be often I shall not be putting this box across this map to distinguish it from the distinguish the actual map from the matrix representation thereof. Okay. So, when I say image of A, yeah, you can read it as the actual image of the linear map, or you can sometimes also often later on read this as the image of a matrix. Okay. So, I will not always be putting this box to call it a matrix. Later on, more often than not, we shall be directly dealing with matrices, because those are the most common type of vector spaces, the n tuples of numbers, right. Okay. So, just a statutory warning, do not get alarmed if I do not always put a box across these alphanumeric variables to distinguish matrices from linear maps. Okay. So, when I am saying this image of A, I am just basically talking about the linear map here, right. So, what is this linear map? So, you see, if A is a linear map from V to W, then this image of A, it is basically nothing but a span of AV1, AV2 dot 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 till AVN, where V1, V2 dot 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 till Vn is a basis for the vector space V. So, what do I mean by that? There is also an alternate definition to this, which we shall see shortly. What it essentially says is that, well, what you do when you try to find out the image of a linear map is the following: take a basis, preferably an ordered basis, but in this case it is not absolutely necessary unless you are going for the coordinate representation. So, take a basis in the domain, get this linear map to act on each element in that basis, right, and then you have a set containing as many elements as the dimension. Again, we are dealing with finite dimensional vector spaces mostly. So, containing as many elements as are there, or as the dimension of the domain, right. So, here the dimension of the domain V is considered to be n, therefore, the basis for V contains n elements, and therefore, the set that you constitute contains n elements from AV1 to AV2 through all the way till AVN. And then you know what a span is, we have already defined it in a previous lecture, right. So, basically you take all possible linear combinations of the elements in this particular set starting from AV1 through till AVN, these n elements, and that would be it. You know, a span is a vector, is a subspace. So, since the image is defined in this fashion, the image will naturally, so remember this image is basically associated with a linear map. So, we have now got a subspace that is associated with a linear map, and that is of course described in this fashion, and because of the fact that we have shown in the previous lecture that a span is going to be a subspace, so also is going to be this image a subspace. There is an alternate definition to this image, which most linear algebra textbooks would probably call as the primary definition of an image, right. So, an image is basically going to be, so let me give the second definition of this image. Again, remember that when we are talking about the image of this linear map, it is basically a linear map from the vector space V to the vector space W. So, this image is basically going to be a collection of all such elements in the vector space in the codomain W, such that there exists some vector V in the domain V satisfying the relation that when you get this linear map to act on this fellow V in the domain, you will get W. In other words, every element in the image of a linear map has a pre-image. Okay. That is to say that for every element that you pick in the image of a linear map, there exists at least some element in the domain which gets mapped to this fellow in the image. Okay. So, quite clearly by the very definition, because you see every element in the image belongs to W. So, quite clearly then the image of A is contained in W. Okay. This leads us to the following definition then: if it is not just contained but also equal to. So, if the image of A is equal to the codomain of A of the linear map, then the map A from V to W is said to be onto or surjective or surjective, as you might pronounce it. Yeah. So, those are the names by which we generally call such maps, onto. It means that for every element, as I described, every element in the domain, in the codomain W, there exists a pre-image, there exists at least one element, if not more. So, if it is a many to one map, yeah, then, well, you do not know if multiple objects might map to the same element in W, right. We are not guaranteeing that that will not be the case. We are saying there is at least one element in V which through this linear mapping gets mapped to this element W. And now, if every element in W has at least a pre-image, yeah, then you say it is an onto map, right. So, the entirety of this codomain can be covered as if, right, with mappings of elements from V. So, that means I say that you pick me up any object, any vector from the codomain W, and there must exist some object or some vector in the domain V such that it gets mapped through this linear map to this arbitrary object that you have given me from W. Yeah. If that is true, then it is said to be a surjective mapping or an onto mapping. Okay. The second most important definition or the important subspace that we can come across when we are dealing with linear maps is the so called kernel. So, then we have another map, another subspace corresponding to a linear map. The moment you define a linear map, immediately you have these well defined as well, that is a kernel. So, what is the kernel of a linear map? Well, remember the image was a subspace of W, that is the codomain, but the kernel is going to be like a dual, it is going to be a subspace of the domain, that is of V. Okay. So, what is the kernel? You pick out some V from the domain V such that when this linear map acts on this object, yeah, when it acts on this object, so of course, yeah, when this acts on this object V in the vector space V, it maps to the 0 element in the vector space W. Okay. So, the collection of all these fellows in the vector space V in the domain V such that they get mapped to the 0 element in W, yeah, that is what the kernel is all about. So, quite clearly again from this definition you will see that it is going to be a subspace of V. Okay. Okay. Now, interestingly, if kernel of A is just the set containing, okay, if kernel of A is just the 0 element in V, which is of course a subspace, no, the 0 element in a vector space is the smallest subspace you can get, right. Smallest means its dimension is 0, right, because you do not need any vectors to span it, yeah, it requires no elements to span it. So, its basis is the empty set. If its basis is the empty set, then the cardinality of that basis is 0. So, this is in that sense the smallest subspace in any vector space, the 0 subspace, right. So, if kernel of a linear map is just the 0 element in the domain, then A from V to W is said to be 1 to 1, or the other name, that is injective. So remember, onto was synonymous with surjective. Now we have 1 to 1, which is synonymous with injective. What is the consequence of this? Just try to think about it for a while, right? What happens if the kernel is just the 0 element? Or rather, what if the kernel is non-trivial? So suppose this is not true. Suppose kernel of A is not equal to 0 element. So that means it contains some non-zero element. That means there exists V belonging to V such that V is not equal to 0, and of course the 0 in the V, and AV, so let us call this V naught. Okay. There exists some V naught in the domain V such that V naught is not equal to the 0 element, and yet when this linear map A acts on this element V naught, it leads to the 0 element in W, right. Then what does it say? It says that as a consequence, if we have V in V such that AV is equal to W belonging to the codomain, then we also have AV plus V naught is equal to AV because of the linearity of the map plus AV naught is equal to just AV. Why? Because this part, remember, by its definition is just the 0. Yeah, so this part is just the 0 element in W. Therefore, this is just 0 element in W is equal to AV, which is equal to W. So then this means for any element W belonging to the image of A, listen very carefully to this and try to pay attention. Look, when I said if we have a V belonging to V such that AV is equal to W, this is just an alternate way of saying that W belongs to image of A, no? Right? Because of the fact that W belongs to the image of A, I can guarantee that there does exist some V such that this V gets mapped to W. So that means now if we hearken back to this idea, then what we conclude here as a consequence is that for any element W that you pick in the image of A, yeah, there exist more than one elements. There exists more than one elements in V such that A V, say more than one elements, we call this V bar. V bar in V such that AV bar is equal to W. Why? So that means this is not going to be unique. Why? Because every time you give me some element V, I can just add this non-zero element that belongs to the kernel, and I can still get the same result, because once I add some element belonging to the kernel of a linear map to any element V, and then I let this linear map act on this resultant sum, yeah, it would have no effect as if I have not added the kernel, because any element belonging to the kernel gets automatically just mapped to the 0 element, right. So therefore this non-uniqueness comes in, and therefore it fails to be 1 to 1. So that is why it gets its name, right. So this statement that I have made here, I hope that now you see that in order for a mapping to be 1 to 1, you must have that this kernel is just the trivial vector space, right. So we have shown that it is necessary, right. We have shown that it is absolutely necessary that this kernel should be trivial. If this kernel is non-trivial, then this mapping cannot be 1 to 1, it cannot be unique. There will be multiple elements, yeah, multiple elements in V which will map to any element in the image of the linear map A, right. Is this also sufficient? So think about it. Again, I am not going to walk you through this, I am maybe just going to slightly walk you through this, but not going to really write this down. Think of it. What do you need in order to prove that it is sufficient? You have to show that if the kernel is indeed trivial, yeah, then there cannot be two distinct elements in the vector space V which map to the same element in W, right. So assume without loss of generality the contrary to be true, that is, you have V1 and V2, both of which get mapped, which are distinct, V1 is not equal to V2, and both of which get mapped to the same element W, right. Then what do you have? Then you get V1 minus V2, which is a non-zero element because V1 and V2 are not equal. So this V1 minus V2, and this is also an element in V itself because you know the vector space V is closed under addition. V1 belongs to V, V2 belongs to V, because minus V2 is an additive inverse of V2, so minus V2 also belongs to V, right. Follow these steps, write them down, write this down, practice this. I am not going to write this down here, okay. Here is the line of reasoning. Let V1 and V2 be two distinct vectors in the vector space V. Because V1 and V2 both belong to the vector space V, therefore minus V2 also belongs to the vector space V due to the existence of additive inverse. And now because minus V2 belongs to the vector space, therefore minus V2 plus V1, that is the sum of two elements in vector space V, because of the closure under addition property of a vector space, that also belongs to this vector space. Because V1 and V2 are not equal, therefore V1 minus V2 is a non-zero vector. So therefore, when you get this A, this linear map to act on V1 minus V2, yeah, then you get on the right hand side AV1 minus AV2, on the left hand side you get A acting on V1 minus V2, but on the right hand side AV1 and AV2 both map to the same element W. So AV1 W is equal to W, AV2 is equal to W, and W minus W is basically the addition of the inverse of W with itself in the vector space W. So you have A acting on V1 minus V2 yielding 0 in W. So therefore V1 minus V2, this element belongs to the kernel of the linear map, because when the linear map A acts on V1 minus V2, it leads to the 0 element in W, okay. But what do we know about V1 minus V2? V1 minus V2 is clearly, because V1 and V2 are distinct, V1 minus V2 must clearly be a non-zero element. So a non-zero element in the vector space V, when acted upon by the linear map, leads to the 0 element in W, yeah, right. So that means that the kernel of A, the linear map, is non-trivial, alright. So if you have two elements that are distinct and yet they have to map to the same element, right, then the kernel of this linear map must be non-trivial, right. So therefore you get to see that this is both necessary and sufficient, right, yeah, because now you see that it suffices, no. Why is it sufficient? I have just proved the contrary, no, that if you first here I assume that this is non-trivial, and then I showed you that there will be two distinct elements that map to the 0, map to any element, okay, right. So it is not a one-to-one. So if the kernel is non-trivial, then you will certainly lose the one-to-one property, right. And if the kernel is, and the other argument is that if you have a mapping that is not one-to-one, then the kernel also must be non-trivial. So it goes both ways. If a mapping is, if a mapping has a non-trivial kernel, it cannot be one-to-one, yeah, and if a mapping is not one-to-one, then it cannot have a trivial kernel, yeah, its kernel must be non-trivial. So it works both ways. These are equivalent notions therefore, right. And this is very important because now you can relate this to the knowledge that you have acquired about the solution of linear systems, right. You see that when you try to solve for these equations like Ax is equal to B, it is the one-to-one property that allowed you to get a unique solution, whereas the on-to property that guaranteed the existence of a solution. So if for example, the mapping was not onto, yeah, then you could not have picked out any B vector. So, suppose now again, now I am going to just take a brief digression. Suppose here now I am talking about the matrix theory case, right. So, A and B, this is a vector. So, this is a matrix, let us say in R m cross n, right. This is a unknown in R n and this is a known vector in R m, right. So, if this had to have a solution, then of course, this B, yeah, this B needs to belong to the image of the matrix A. Yeah, the matrix is the same as a linear map, no, over Euclidean spaces, right, like Rn. So, therefore, if this has to have a solution, the existence of the solution is predicated upon the linear map being onto or surjective. The uniqueness of the solution is predicated upon the linear map being onto. So, if you require an onto, if you require a unique solution to exist, your map had better be both injective and surjective. So, if Ax is equal to B has to have, so has to have means this is the existence question and the next is the uniqueness question. Then A must be both. So, for existence you need surjection, surjective, and for uniqueness you need one-to-oneness, that is injective. So, a map that is both surjective and injective, map that is both surjective and injective is called bijective. Okay. So, if you have both surjection and injection, then the map must be a bijection, or the linear map must be a linear bijection. Okay. So, that is a very, very important property. Okay. So, the next important concept that we are going to learn about is of course going to have to deal with these notions only. So, it is going to be the so called rank nullity theorem. Okay. So, quite simply put, so in whatever time is left today in today's lecture, I am going to just give you a brief idea of what rank nullity is all about, and in the next lecture we shall see a very brief sketch of the proof. Yeah, I will not again get into a very great detail of this proof because that will be again part of some standard linear algebra course, but here is what it says. So, suppose you have this linear mapping from the vector space V to the vector space W, right. So, here is what the rank nullity theorem says, and suppose V and W are both, again without loss of generality, unless I mention otherwise, you always assume these to be finite dimensional vector spaces. Okay. So, now if you consider them to be finite dimensional vector spaces, then what we can say is that this is what rank nullity theorem says, that the dimension of V is going to be equal. So, V is, remember, the domain is going to be equal to the dimension of the image of A plus the dimension of the kernel of A. But please do remember that the image of A is a subspace of W, the codomain. The kernel of A is a subspace of V, the domain. So, on the face of it, if you directly look at this, it might seem a little difficult to connect at first. Yeah. But now I will use a term with which you are most probably familiar by dint of your introduction to matrix theory and its related notions, that is, this dimension of this image of A is often termed as the rank of A. Okay. And this is often termed as, the nullity of A. So, it turns out that in layman's tongue, if I want to put this, is going to be like the sum of the rank and that of the nullity of this linear map A from the vector space V finite dimensional vector space V to the finite dimensional vector space W is going to be exactly equal to the dimension of the underlying domain, that is V, alright. What does this essentially tell us? In some sense, I mean, in a little abstract notion, this is like, restricting the freedom, yeah. If you think of it like, what is the image of A and what is the kernel of A, right. So, if the kernel is, for example, trivial, yeah, then you have the dimension of V being equal to the dimension of the image of A. But remember, what is the image of A in such a case? The image of A is a subspace of W, right. So, that means the dimension of V, that is the domain, is equal to the dimension of a subspace of W. So, that means the dimension of W is at least equal to that of V, if not greater, right. So, that means this mapping, linear mapping, maps from a lower dimensional vector space to a higher or equal dimensional vector space, yeah. So, what does that mean? That means that vector space W has a larger number of elements in its basis, yeah. So, think of it in this fashion. So, you can always pick out some element in W, yeah, and it may be that, well, because V is not as rich as W, again loosely speaking. So, it might happen that you do not have a solution for every element that you pick in W. There need not exist some element in V such that this element in V gets mapped to that particular element you have picked in W. So, that solution may not exist, yeah. But if it does exist for that element, then it will be unique. Why? Because dimension of kernel of A being 0 implies it is an 1-to-1 mapping, right. So, if the solution exists, then it is going to be unique, but the solution may not exist, right. On the other hand, now think of it in this way, if it is a surjection, if it is an onto mapping, then the image of A is exactly equal to W. So, no longer is it a proper subspace of W, but it is equal to W. So, the dimension of V in that case is equal to the dimension of W plus potentially some non-zero value, non-negative value at least, because the dimensions are non-negative values, right. So, in such a case, it turns out that as if the dimension of V is at least equal to or greater, for a surjective mapping, the dimension of the domain, that is V, is at least equal to or greater than the dimension of the codomain, that is W. Yeah. So, there are more elements, at least V, the vector space V appears to be richer, right. So, in that case, every element that you pick in W will find some element in V such that this element in V gets mapped to the element in W, but because V is richer, there might be some other elements in V also which, when added to these elements in V that map to the element W, yeah, make no difference. That is, multiple elements in V might map to the same element in W, okay. At least intuitively you can get a feel for this from this relation, okay, and that is very important, okay. So, from this relation, this rank nullity relation that I have written here, it is important that you get a feel for why the injection and surjection properties are also somewhat hinted at or indicated in this particular relation that I have jotted down. So, in the next lecture when we start, the first thing we shall see is some sort of a derivation of this rank nullity theorem, and then we shall quickly move over to things like a change of basis and how it affects a linear map. And as it turns out, this is something that you have already done in your earlier control theory courses, if not a linear algebra course earlier, because when you talked about this diagonalization of a matrix for a state space representation and so on, essentially what you have done is a change of basis, okay. So, we will see that in a slightly more formal fashion maybe, but all that in good time in the next lecture. Until then, take care.